Harmonics. As we connect more electronic devices to our power systems, the quality of the power becomes more important. Quality can be defined in many ways. Two characteristics which are very desirable to power systems are stable voltages and undistorted waveforms. You have probably heard the term harmonics, and from this term, the following questions arise. What are harmonics? How do they affect single and three-phase circuits? What are the symptoms of harmonics? How do I address these symptoms, and how do I solve the problem? The concept of harmonics is a method used to analyze and explain distorted waveforms found in computers, electronic ballasts, variable frequency drives, power systems, other equipment which have modern transformerless power supplies. In the case of an AC circuit, the voltage applied is a sine wave which operates at 50 Hz. Generating authorities go to great lengths to control the generation of voltage, producing a sine wave that has relatively constant amplitude and constant frequency. If this voltage is applied to a linear device, such as a resistor, the magnitude of current may be determined by the applications of Ohm's law. Expressed graphically, the current also takes the form of a sine wave. Ohm's law dictates the frequency of the current wave will also be at 50 Hz. Since an applied voltage sine wave will cause a sinusoidal current to be drawn, systems which exhibit this behavior are called linear systems. Examples include incandescent lamps, heaters, and motors. Some modern equipment, however, does not fit this category and gives rise to what are known as nonlinear systems, which are computers, variable frequency drives, VFD, electronic ballasts, and uninterrupted power supply systems, or UPS. In these systems, the resistance is not a constant and in fact varies during each cycle of the applied sine wave. This occurs because the resistance of the device is not a constant. The resistance, in fact, changes during each sine wave. The power supply of these systems contains solid-state devices such as power transistors and thioresistors, which is silicon-controlled rectifiers, or SCR, or triacs. These circuits in which these devices are connected draw current in pulses. When voltage is applied, the current drawn is zero until a critical firing voltage is reached. At this firing voltage, the circuit allows current to be conducted. This current typically increases over time until the peak of the sine wave and decreases until the critical firing voltage is reached on the downward side of the sine wave. The device then shuts off and current goes to zero. The same thing occurs on the negative side of the sine wave with the negative pulse of current being drawn. The current drawn then is a series of positive and negative pulses and not the sine wave drawn by the linear system. Some systems have different shaped waveforms such as square waves. These types of systems are often called nonlinear systems. Once these pulse currents are formed, it is difficult to analyze their effect. In order to solve this problem, we turn to harmonics. Simply stated, it can be proved any periodic waveform can be expressed as a series of sine waves and varying frequencies and amplitudes. That is, we can create a series of sine waves of varying frequencies and amplitudes to model these series of current pulses, in which the frequencies used are multiples of the fundamental frequency of 50 Hz. These multiple frequencies are called harmonics. The second harmonics is 2 times 50 Hz, which is 100 Hz, and the third harmonic is 150 Hz, and so on. In three-phase power systems, the even harmonics, so second, fourth, sixth, etc., cancel. So we only need to deal with the odd harmonics, 3, 5, so on. Regarding the third harmonics, there are 3 cycles for each single cycle of the fundamental. If we add these two waveforms, we get a non-sinusoidal waveform. The resultant now starts to form the peaks that are indicative of the pulses drawn by switch mode power supplies. If we add in other harmonics, we can model any distorted periodic waveform, such as the square waveform generated by UPS or VFD systems. The pulses of square waves or other distorted waveforms are what we actually see if we connect an oscilloscope to the circuit. These current pulses will also begin to distort the voltage waveforms in the supply system. This voltage distortion can cause premature failure to electronic devices. On three-phase systems, the three phases of the power system are 120 degrees out of phase. As a result, 50 Hz current actually cancels in the neutral. For balanced 50 Hz currents on the three-phase conductors, the neutral current will be zero. The neutral current, assuming only 50 Hz is present, will never exceed the highest load phase conductor. Thus, our overcurrent protection on the phase conductors also protects the neutral conductor. When harmonic currents are present, the situation is different. The third harmonic of each of the three-phase conductors is exactly in phase. When these harmonic currents come together in the neutral, rather than cancel, they actually add. Therefore, more current in the neutral conductor than on phase conductors, the neutral conductor is no longer protected. Harmonic currents create heat, which over a period of time will raise the temperature of the neutral conductor and overheat the transformer that supplies the power supply. These are the most obvious symptoms of harmonics. Other symptoms include nuisance tripping of circuit breakers, malfunction of UPS symptoms and generator symptoms, metering problems, computer malfunctions, and overvoltage problems. Several remedies are available to address these symptoms. Oversizing neutral conductors. In three-phase circuits with shared neutrals, it is common to oversize the neutral conductor up to 200% when the load served consists of nonlinear loads. Using separate neutral conductors. On three-phase branch circuits, another philosophy is to not combine neutrals, but to run separate neutral conductors for each phase conductor. Oversizing transformers and generators. The oversizing of equipment for increased thermal capacity should also be used for transformers and generators which serve harmonics producing loads. Special transformers. There are several special types of transformer connections which can cancel harmonics. For example, the traditional delta star transformer connection will trap the triplan harmonics, 3rd, 9th, 5th, 21st, etc. in the delta. Additional special winding connections can be used to cancel other harmonics on balanced loads. Filtering. While many filters do not work particularly well at this frequency range, special electronic tracking filters can work very well to eliminate harmonics. These filters are presently relatively expensive but should be considered for thorough harmonic elimination. Special metering. Standard clamp-on ammeters are only sensitive to 50 Hz currents, so they only tell part of the story. New true RMS meters will sense current up to the kilohertz range. These meters should be used to detect harmonic currents. The difference between a reading on an old-style clamp ammeter and the true RMS ammeter will give an indication of the amount of harmonic current present. Measures described before only solve the symptoms of the problem. To solve the problem, we must specify low harmonic equipment. This is most easily done when specifying electronic ballasts. Several manufacturers make electronic ballasts which produce less than 15% harmonics. These ballasts should be considered for many ballast retrofit or any new project. Until low harmonic computers are available, segregating these harmonic loads on different circuits, different switchboards, or the use of transformers should be considered. This segregation of dirty and clean loads is fundamental to electrical design today. Classification of harmonics. Each harmonic has a name, frequency, and sequence. The sequence refers to phase of rotation with respect to the fundamental that is an inductor motor. A positive sequence harmonic would generate a magnetic field that rotated in the same direction as the fundamental. A negative sequence harmonic would rotate in the reverse direction, and zero sequence harmonic are the odd multiples of the third harmonic called triplans. The first 9 harmonics, along with their effects, are stated below. Fundamental is 50 Hz, which is positive. Second is 100 Hz, which is negative. Third, 150 Hz, 0. Fourth, 200 Hz, positive. Fifth, 250 Hz, negative. Sixth, 300 Hz, 0. Seventh, 350 Hz, positive. Eighth, 400 Hz, negative. Ninth, 450 Hz, 0. Even harmonics disappear when waves are symmetrical. A positive sequence has a rotation of forward, the effect, heating of conductors, circuit breakers, etc. Negative sequence has a reverse rotation, affects heating of conductors, circuit breakers, and problems with the motor. Zero sequence, which has no rotation, heating of the conductors, circuit breakers, they add in a neutral for a three-phase, four-wire system.